So first of all, it's a pleasure to be back here at ISC, and I look forward to my next 3 weeks here at the Institute. I arrived yesterday, so I'm very happy that I immediately can be participant in the in-house symposium. However, I arrived yesterday, so that means that I do not have a magnificent talk such as the many we have seen, but sort of 2 half-baked talks, each of which is more of an advertisement than a talk. So I hope this will you will bear with me for this. It also has 2 titles which are not entangled, at least I don't think so, but let's see. So the first one is on the, it's not quite, the title is not, okay, there's some, anyway, this is the, I think the titles have dropped, but the titles are not so important. So this is about, the title was the CERN strategy, which is the process by which the European particle physics community defines the future of CERN and its member states with India, let's not forget. I'm involved with this as a member of the CERN Council for the Netherlands. I'm also a member of the strategy group, and at the moment also I'm still for a few months the vice president of the council. So this strategy update, this is what I want to talk about in the first half. It's an intense 2 years well-regulated process. For those of you who don't know how this goes, it started in 2005, but it's been updated in 2013, 2020, and the new update started 2 months ago. So we really are now in the early stages of the next strategy, and this will be an important one, perhaps the most important of all of them. So it is certainly a bottom-up procedure. There's lots of room for input. The first deadline for input is in March of next year. I'm not sure if India as a community will provide an input, or it will go per experiment. It's something that one might want to consider. And when there is a strategy, the result wields considerable authority. Many strategies are nice documents for the drawer that you now and then look at when you want to be inspired. This is actually something that people follow, that CERN follows when it sets up its budget. So it's really, it has a lot of authority. So it's a strict guide how to spend its resources. However, should there be a big project, that has to be separately approved. Now, to understand this strategy and how it works, maybe it's good to remind you how CERN is governed as a multinational organization. So the highest authority is the CERN Council. It sets all major decisions, approves large programs, budgets, and reviews expenditures. It has more, but 2 of the most important subcommittees of Council are the Scientific Policy Committee, which advises the Council on science issues, and the Finance Committee, obviously, because it's about money. The Director General, with the Directorate, manages the lab. So they're perhaps the most famous, but formally they're the Secretary of the Council and not the boss of CERN as such. And this structure is really enshrined already in the Convention of 1953. So there are 24 member states. Now, since this year, the 24th one is Estonia. And here, this picture is the flag-raising ceremony of Estonia in mid-October on a rainy day, as you can see. Here's the President of Estonia, there's the Director General and the Ambassador of Estonia in Geneva, and here's me. I was replacing the President at the time, so I was helping raising the flag for Estonia. It was kind of a nice event at CERN for that. So per member state, there were typically 2 delegates, 1 government, 1 scientist, and as I said, it votes on all these things. 10 associate member states, among which is India since 7 years, I think. And the members here are Mr. Sunil Ganju and Professor Ajit Mohanty, both from DAE, which is the lead agency of the 2. There are also observer states, Japan, the US, the lab in Dubna has been suspended, and Russia at the end of this month will be discontinued. The Council meets 4 times a year, often more for special occasions. One of these was this week. On Wednesday, I was in CERN to elect Mark Thompson here as the next DG of CERN to start in 2026. Now, as I said, the strategy was first initiated by Council in 2025, interpreting this element of the CERN Convention to act as the representative for European particle physics, not just the lab in Geneva. Again, the strategy is not resource loaded, so this whatever comes out of the strategy, such as a future collider, will require a separate decision. Now, the last strategy in 2020 resulted in these booklets. So these are the front covers, a short version and a slightly longer version with a bit more information. Not too long, maybe 20 pages, 20 statements, very clean, concise, and people actually quote them constantly. So here's a few of those statements. Here's the first one. Essential for particle physics in Europe, for CERN, India is part of that, to propose a new facility after the LHC, particularly a Higgs factory. And at the time, the charge was start investigating the feasibility of such a thing, particularly the technical and financial feasibility for a machine that starts in E plus E minus and goes on to a Hadron Collider, the FCCHH, which was already earlier in the talks. And this feasibility study is what I'll be discussing a little bit now. And the feasibility should establish as a global endeavor and completed of this time scale soon. And in fact, it is. We're now beyond the midterm point, and the midterm report was fully assessed. There was a report, a short version, 700 pages. I shudder to think what the final version will be. But there's an executive summary of 50 pages if you want to have a quick read. So, these really a very thorough job, and I'll give you some highlights of this. Now, what are the things that the midterm study looked at? Lots of stuff, actually, not just what physics does it do, that's what we all tend to do, but there's lots more going on that you have to show. Is it geologically feasible? Can you dig a tunnel that won't collapse or fill with water? What about the stuff that you dig out? Can you do it environmentally responsibly? Where do you put the ring? I mean, what is the access to where you put the ring? Do you access it with roads, with power, with water, all the stuff, the infrastructure you need? How about administrative processes? There were 2 host states. There's lots of member states. How do you deal with that? The design of the collider itself and the injectors, the lower energy things that pump the particles into the machine, the sustainable model of operation, cost, very important, and not just what it costs, how do you fund it after you build it? How do you get the resources? And the physics case, of course, is a very important part of it. I'll just highlight 1 or 2 of these. We won't have time for a longer one. Turns out, after lots of study, there was a unique solution to put the ring precisely here on the border of France and Switzerland, and you cannot move it anymore a little bit. This is really where it is. It is not 100 kilometers, but 90.7. And this really fully optimizes all the requirements for power, for underground, for road access, train access. So this is it. If it all gets built, this is it. 90 kilometers. You can still modify a little bit up and down and tilting it a little bit. If you hit a pocket of water, you can still do this, but you cannot move it laterally underground. Lots of drilling is happening, some even in the bottom of Lake Geneva, just to see is the ground right. And most of it is almost all molasses, which is good digging material. And if it all goes well, civil construction could start in 2033. And here is a more schematic view. There are 8 surface areas here indicated by these shafts. The tunnel is 5.5 diameter, and every 0.1 meter costs a lot more money, so this is optimized. And at these 8 points, the idea would be at these 8 points you put down 8 TBMs. These are tunnel boring machines. So you let them go down and they start digging and meet each other at the next access point. So you don't do one all the way, you do 8 sections independently, maybe by even independent contractors. So there's lots of stuff that has to be done, full 3D underground model construction. So here is a bit of the machine parameters. There's 4 interaction points, H surface, so room for 4 experiments. This will be important for the HH version. If that ever gets built, you need the experimental halls for that. And then there's lots of data here, which I will certainly not go through. But here's some key elements, depending on whether you do lots of Z boson production, a WW threshold, the Higgs boson together with the Z, or the TT bar production, each of which has a higher energy and lower luminosity. But the numbers are impressive. So in all the electroweak variables, you get 10 to 50 factors of improvement on currently known results. 10 factor improvements model independent on Higgs couplings. 10 times the Bell-2 statistics for bottom, charm, and tau. Effective theory limits up to 70 TeV, etc. So there's a lot of strong potential here. So a bit of funding model idea, so I skipped many other aspects. So how do you get the money for this? The total amount for the full program was 15 billion Swiss francs. By now that's more, inflation, etc. And most of it comes from Z, W, and ZH. TT bar is $1.5 million more. And so this is the full cost for all the different parts, including 10% contribution of CERN to the experiments. So this is what has to be found. This cannot be paid by the CERN regular budget. We need extra money for that. That could be from extra contribution by member states. We need at least 400 billion outside the CERN budget. Oh, we can continue. Can you hear me still? Okay. Okay. This could come from the US, from the government of the US, although who knows after this week. There were also major contributions expected from the Silicon Valley. There are some very rich people who are keen on contributing actual money to this project. So I think these are some of the ways that can make this machine work. Now, key purpose to remind you is Higgs factor. We measure this one particle that is so unique that we don't know, measure it extremely precisely, its mass, its width, and all its couplings. That is something that we should do. Secondary, but still important, really upgrade the stress test standard model really to a great extent at these other poles. 4 interaction points really help with the velocity. That's a big advantage over linear collider for one thing, right? That you can have 4 interaction points. This is the provisional timeline. This is what we're in now, including the feasibility study and the strategy. If it gets approved by the strategy update, we may decide we won't do it. If it doesn't seem feasible, if it is feasible, it will be hopefully approved by CERN Council around this time, etc., and then you get the next operations. It takes a while. Unfortunately, things are so big, they take a while. So at this stage, what we can show is that there are no showstoppers identified at the midterm point. Since the midterm point, this is really nice news, they have figured out how to set up the initial stages such that you can quickly switch between running on the Z pole, at the ZH, and at the WW. Instead of first 4 years at the Z pole, and then that would be somewhat boring. This is much more interesting to quickly be able to switch. So this is a real advantage. And the final report is in a few months. Now, what if not? The header title that's missing is what if there's not an FCC? Well, then you can think of CLIC, ILC at CERN, or go straight to the Hadron Collider. This will be an important variable. What will China decide regarding the CEPC? And then what about Muon Collider? These are exciting machines, but not ready for prime time, I would say. They're still in the R&D phase, as the US has decided. So this is a bit the present status of the future of CERN. I'm happy to talk about it with you also in the next weeks. Second part, completely different. This is on resurgence. Some of you, this is now physics, or mathematical physics, rather than what I just talked about. And this is really, I should say, not really my main topic of research. It's kind of a nice collaboration with Marcel Vonk at the University of Amsterdam, where we have a PhD student, Koenraad Marinissen. And let me tell you, what I want to do is tell you a little bit what resurgence is, and then as an advertisement, and not go in detail through the paper. Here's the nice part. The perturbation theory descriptions in quantum field theory, as you know, often are not convergent but asymptotic. That we all know, we can live with it, we can still make precise predictions. But this may indicate the presence of non-perturbative contributions. We also know we don't have that in the regular coupling expansions. And resurgence is a set of methods to precisely extract these non-perturbative contributions in a using very interesting set of tools developed in the 1980s by mathematician Jean Écalle. And it uses tools like alien calculus, bridge equations, large order relations, which I will not explain. There's a nice Quanta magazine article on it to give you a sense of what this is. So here's an example, just to give you a sense of what resurgence does. Let's look at this differential equation. The solution is always the sum of a particular solution and one of the homogeneous equation. Now, substitute this series in here, and you can quickly show that the coefficients Cn behave like n factorial. That's bad. Right? That means that this will not converge for any x. Even if I take x 10 to the minus a Google number, this will not converge. Right? I think this will diverge eventually. The homogeneous equation has a very different solution. It goes like e to the minus 1 over x. Think of x as the coupling constant. So this is, here you see a bit of a non-perturbative effect appearing. So now, and here's a set of mappings you can do. Here's your usual perturbative expansion. If you take a Borel transform, that means you can divide every coefficient by n factorial, and now suddenly it becomes tractable. However, of course, you've made a major change. You can now do the sum, and if you then go back using the inverse Borel transform, which is sort of a Laplace transformation, and you can then expand around this, you get this again. But in the meantime, you can actually do something significant. So here we have the situation with the perturbative solution and the homogeneous non-perturbative solution. Can we somehow, using resurgence, find both? So Borel summation leads to this result. It's just a geometric series. And the inverse Laplace transform instructs you to integrate from here to there, but there's a pole, a t is 1 here. So you either go above or you go below, but you must do something. Now, that's what this is, right? This is the integral from 0 to 1. So clearly this is an ambiguity. And this ambiguity, the difference of these two curves is precisely e to the 1 minus x. So going from this contour, moving the contour to this one, picks up the non-perturbative contribution. And this is called Stokes transformation that really does that. So here's a more general form. That's with a pole. You can even have also a logarithmic singularity where you have branch points. And then if this is from your perturbative calculation, you find that in fact if you do this move from the contour below to the contour above, you pick up non-perturbative sectors like this. So the non-perturbative sectors with e to the minus a over x, e to the minus 2a over x if there are more divergences. The non-perturbative sectors resurge. They come back they come back and reveal themselves. So the real object that you should look at is not the perturbative series, but the trans series, which is the perturbative series and all these non-perturbative sectors. And this object is one that is central in resurgence. And the goal is then to find these ends and what these series are. Now the nice thing is that the asymptotic behavior of this series here, in fact, reveals this. So if you look at the very large order behavior here, you can actually derive these fn's. And that's a real concrete relations that tell you what are these non-perturbative sectors. You just look at the large order behavior of this and you can actually find formulas for this. So that's a real concrete map from the asymptotic regime of the perturbative series to the non-perturbative sectors. And this is really the major power of resurgence. Now, what we looked in this paper is something in particle physics. It's one of the first times this was done. It's not exactly particles, but an important ingredient, the so-called Adler function. If you have a Fourier transform of a correlator of two vector currents, of two psi bar psi currents, this is the typical Adler function. You see this in all your quantum. This is a typical self-energy function, and the derivative is the Adler function. This has no UV divergences. And these are the Feynman diagrams for this self-energy vacuum polarization diagrams. And what we did was we inserted here bubble chain propagators with lots of fermion loops, n fermion loops in here, and those provide n factorial growth, so which have to be Borel summed. We did that, and that gave you singularities in the Borel plane. And as we just saw, that is a pathway through resurgence to non-perturbative sectors. At the two-loop level, this is an exactly known result. You can nicely write it like this in the complex U plane, and you can sum this and get a very nice exact result. This is a very simple trans-series structure. We looked at lots of three-loop results and wanted to investigate what is the new non-perturbative structure thanks to going to three loops. And we in fact found a two-dimensional non-perturbative sector pattern, the so-called alien lattice. Each box here is a new non-perturbative sector. And so this is really what the resurgence analysis tells you that was not known before. So it's quite powerful. So you can actually use in resurgence operators as alien derivatives to move from one sector to the next non-perturbative sector to the next non-perturbative sector. You can also move back. So there's a lot of resurgence motions among the space of non-perturbative sectors. So already, this is not new. It has already many achievements in low-dimensional models in string theories, particularly topological string theories, matrix models, and I think we were the first to look at resurgence for particle physics, but only the very first step. There's many more applications we hope to do. So that's a bit the two advertisement blurbs I had to give. Thanks.
Sort of visibility, can you see it in some experiment or some? It's a diagrammatic calculation, no? Right now.
Right.
Yeah.
No. So the form that so this, if you think this as the QCD coupling, right? If you work this out, this is lambda squared over q squared. This e to the minus e of x becomes lambda. So that's a real power correction, and that you could measure, for example, in event shapes and various other variables. They're small corrections, so they're difficult to measure. But things in like tau decay or in other things you can really measure precisely, they could start showing up. So it is initially it's theoretically interesting, but it might have some experimental relevance, particularly because we strive for so much precision.
So in that differential equation you are talking about.
Sorry, it's not. Oh.
Hello? Yeah. Am I heard? Yeah, I think. Yeah, so the differential equation you have showed this equation. So, I mean, is there any particular reason that, above the cart and down there, this thing, so that should be the other solution. Is there any particular reason, or it's just happening to be such?
Well, this is it. So, if I'm trying to understand your question, so this is a very simple case, right? So, you fix one, and then you move to the others. But in fact, there's many more. There can be many more singularities, and every time you have to change, you take your contour to the next sector.
I feel like this.
Every time you pick up new.
I feel like what is happening here, like you can have your series. There is a after Borel summation, you have this. Pole at t equal to 1. So you choose it above that pole, and you can choose also downstairs there, right? So then you see that the difference of these two are happening to be the other solution. So is there any understanding for that, or it's just happening to be such?
Well, if you choose, so you have to choose with one, start with one, and then see what happens when you go to the other one. Now, if you would say, well, I forget what I just did, I will start with the other one. That gives a consistent answer. You have to make sure indeed that you don't get different answers. What this gives you is an ambiguity, but this C, right? So you have to still fix the C with some external condition. But at least you know a lot about the non-perturbative, including the perturbative series in front. Until now, the state of the art was you could just know the non-perturbative sector, but know nothing about the coefficient in front. Now you know something about the coefficients in front.
Right.
Since there is no other questions, thank you, Professor. Thank you for the nice talk. Then.